Hey guys, welcome to a new video in this artificial intelligence tutorial. In this video we're going to continue with the fourth and the last video in this artificial intelligence and reinforcement learning project that we're currently doing. And the reinforcement learning algorithm that we apply in this project here is the Q-learning algorithm. And we have in the previous videos we have already implemented and talked about the project, and also deployed the agent, and also tried to train the agent that we have implemented in actual code. So we pretty much made the program here, or the project, and finish it up with the code. But in the end here, when we are training our agent, we want to find the most optimal parameters, so we can try to test some of the the training process and see how much expected reward can we get, and can we try to optimize that by tuning some of the different kind of parameters in the Q-learning function. So how can we test and tune the reinforcement learning agent is what we're going to talk about in this video here, and I'm going to show you guys how we can get the data from C++ and how we can get them into Python, and then from Python we can use some different kind of modules to plot the data, and then we can see how does the parameters act when we're training the agent, and then we can go back and tune some of these parameters here and find the most optimal parameters that yields the maximum return. But first of all, remember to hit the subscribe button and bell notification on the video, and also like this video if you like the content and you want more in the future, because it really helps me and the channel out in a massive way, and I'm just really appreciating your huge support on this channel here. So let's jump into the first slide here, where we're just going to have a short recap over the project and what we have already implemented in the previous videos. So we have this environment here where we have these different kind of rooms where we have a predefined reward distributed out in every room, and then our agent is going to learn to take the most optimal path to maximize its reward by only taking a fixed number of time steps here. So it could be for example, we start at room 0 here, and then it will get 5 time steps, or it can take 5 actions before it terminates. So we need to find the best path to maximize its own reward. So it will learn that by just interacting with the environment and having this Epsilon greedy and the exploring and exploitation trade-off that we've talked about in the previous videos as well. So when should a robot explore, and when should it exploit what it already knows by the environment. So this is kind of like a training process, and this is the environment that we have implemented, and we have already trained our agent, and we also deployed it. But now we need to test some of the parameters that is in the Q function with the learning rate and the discount rate, and also the Epsilon decay. So how much do we want to explore in the beginning, and how much do we want to decay that exploring over a number of episodes when we're training our agent. And then we want to use those tests here to find the most optimal parameters to maximize the reward for our agent when it's training and interacting with the environment. So here's just a short preview over the different kind of results that we will get from the test. I'll show you how we can get this data here from C++ and how we can import it into Python. And then I'm going to show you how we can plot these data here and talk about what this data and these graphs here mean, because some of the parameters in the functions also depends on each other. So we're going to talk about how can we choose the best parameters for the Q-learning function by just looking at these results here, play around with the different kind of parameters, and then find the most optimal parameters that we then train our agent on again to maximize its expected return or reward when it's done training. So when we deploy our agent, it always finds the maximum number of reward that it can receive within a fixed number of time steps. So we're done in this Visual Studio here, and I'm going to show you the code for formatting the data to a CSV file, and then I'm going to show you how we can get the information from C++ to a CSV file, and then we can import that CSV file in Python, and then do the data analysis and also the plotting of the graphs in Python. Because in Python it's a lot easier to import some modules and work around with some visualization, and also just testing different kind of parameters, because it's just easy to run, and we can just import data from a CSV file and run the Python script, and then we will just instantly get the results for the training of our agent. So first of all, here in the Q-learning CPP file, I have this function here that can extract the data that we have in C++ here to the CSV file, and then we can later on import that CSV file into Python and then do the data analysis on that CSV file. So first of all, here I just have a CSV file which is comma separated, so all the values are comma separated in the CSV file. So first of all, we're just going to output the number, each episode, number for each episode, and then for each episode we're going to output the expected return per episode and the epsilon value, and also the learning rate for that episode. So we can see like when we're plotting the epsilon decay rate together with our like expected return, then we can see like how the agent learns and like how fast the agent learns, and what different kind of things does the agent learn and how does it affect the agent, and then we can tune some of the parameters depending on the results that we see in the Python script. So this is just a function to get our data to a CSV file from C++, so we can import it in Python. So if we go into the header file here, down here at the bottom, I have 3 different kind of CSV files that we're going to write to, depending on the test that we're doing. So up here, I have the different kind of parameters that we're going to test and tune and try to find the most optimal ones, which will result in the maximum expected return for the agent. So first of all, here we're going to change the gamma value here, or the discount factor. And the first test here we will start at 0.8, and then and in another test we will go for 0.5 and 0.3. So the first test here we're just going to have this gamma value here, and the test results, or like the training results, will be stored in this CSV file here. So now I'll just run the program here, and the agent will now learn for, or like train for 30,000 episodes, and for every episode we store these values for the episode in a vector, and then this vector here, after our training process is done, we just output that vector to a CSV file. So we can see now that the agent has learned for 30,000 episodes, and we can see that the data has been formatted or like sent to a CSV file. So if I hit enter here, it will just go back here, and now in the directory where our code is, now we can then find like the file that we just created. So if I open the folder here in File Explorer, we can see that we have now created this file up here, and it's now updated at this time here. So the Q-learning test is now updated, and we can see like all of these values here that were stored for the training process will be stored here, and then we can load this in here to a Python later on. So we're going to do the same thing here for a gamma rate of 0.5 and also for 0.3, and then we're going to store it in another file and then import that to Python and then do some data analysis on that. So we're now to train the agent for 3 different kind of discount rates, and we're now going to the Jupyter Notebook where we're going to do the actual data analysis. So first of all, we're going to import the CSV module here, so we can operate with a CSV file that we stored the data in C++. And then we're going to use matplotlib here to actually like plot the graphs that we store in the slides as well. First of all, here we have some different kind of numbers that we have to choose for the episodes and also for the split values. Because when we're going to plot these here and we're doing 30,000 episodes, then we don't want to plot 30,000 data points. So we're going to take the average for every 1,000 episodes, and I'm also going to show you an example where we're only going to take, like for example, the 15,000 first episodes, and then we're going to take the average of 100, like average for every 100 episodes, so we can visualize like the process a bit more, and we don't get like a flickering or like a very uncertain result. So this is just for visualization, and also so we get less data points and we don't have to like plot 30,000 data points in our graph. So first of all, here we're going to load in the data from the file, and then we're going to cast it to floating values, because when we had to operate with CSV file, it is converted to a string, and then we need to cast it back to a floating point number. So this is just this cell here. We're going first of all, we're just going to open up the CSV files, and then we're going to read the CSV files line by line. Then we're going to do some processing and then casting the values in our CSV file to floats and store in some list here in Python that we're going to operate with later on. Then we can see if we print the length here of the expected return for the first, the second, and the third test, we can see that we have these 30,000 values here, or data points, which is a point for every, like a data point for every episode that we've trained our agent on. So now here we have this different kind of cells here where we're going to take the average of the episodes. So we're going to do it both for the first 15,000 episodes, where we're going to take the average for every 100 episodes, and then we're going to take the full 30,000 episodes, and we're going to take the average for the first 1,000 episodes. First of all, here we're just going to convert it to a NumPy array where we're going to split like our array into these split returns that we want. So like how many splits we want to, like how many times we want to split our array into like the rewards per 1,000 episodes. So now we will get our NumPy array split into these rewards per 1,000 episodes. So we can go in and take each of those lists here, and then we're going to take the average of those lists, and then we can plot those data points onto our graphs. So first of all, here we just have a for loop here that just runs through all of these rewards here for 1,000 episodes, and then we're going to take take each, and in this array here, we will have an array here with 1,000 elements. So we're going to take like each of these elements here, and then we're going to append it into this average return vector here, or like list. And then we're going to take the sum of all the rewards in the first or in these 1,000 episodes, and then we're going to divide that by the split return, so like how many elements there is in this reward per 1,000 episodes. And then we'll get the average of the 1,000 episodes, and we're going to append that to the return of the average vector here, or like a list. And this is actually like the list that we're going to plot later on when we're going to visualize the data and the data analysis, and then we can plot it in a graph and see like how the agent has performed while training. So we're going to do this again here for like the 3 different kind of tests that we did, and we're both going to do it with the 1,000 episodes and taking the average of those, and we're also going to take it with the first couple of 15,000 episodes, and then we're going to take the average for every 100 episodes. So we're going to do that in these 6 cells here of code. And then down here we have the data for the epsilon and the learning rate decay, which doesn't really matter for this test here, because our epsilon decay rate is just constant and it won't change anything. So we're going to do this for another test where we're going to test the epsilon decay rate and how much we want our epsilon value to decay for every episode. So this is the exploration and exploitation trade-off that we're going to test with these blocks of code here. So if we go down to where we're actually going to plot like the data that we have gained from our agent learning, we can see that here we're going to like just plot it, where we're just going to plot like all the episodes, and then on the x-axis we're going to plot the episodes, and on the y-axis we're going to plot the averages that we just calculated in the cells up above. So the first graph here, or like the first plot here, is the gamma value where it was 0.8, and then we have another gamma value here, which is the blue plot down here, which is the gamma value of 0.5, and we also have it for the green here, which is 0.3. So if you go down here on the plot, we can actually like see the results for our agent training or like learning by interacting with the environment, and then we can see like how this discount factor here affects the agent when it's learning in the environment over the episodes. And we're also going to do this here down here with the first couple of episodes. In this case I just chose, we want to see the first 15,000 episodes, and then we have the averages of each, or like every 100 episodes. So first of all, up here we can see that a gamma value of 0.8, it doesn't return or like it doesn't converge to a very high expected return in the end. So the maximum expected return we can get for having a gamma value of 0.8 is around like 65. But if we choose another gamma value up here, let's say 0.5 or 0.3, we can see that we get a higher expected return, or like we converge towards a higher expected return. And the best one here is a gamma value of 0.3, and we can see that from the graph here, because we can see like we get a nice and steady green plot here that is just like rising until it converges towards the maximum expected return. And this is also like the theoretical maximum expected return that we can get for taking the fixed number of time steps that we chose in this project here. So this is where like we can test some of the parameters in this Q function here, and then we can plot it in this Python script here, and then we can see how does the different kind of parameters and values affect the agent when it's learning. And from this plot here we can just see that a gamma value of 0.8 is not good enough for our agent here if we want to get the maximum expected return, and that is the case for this project and any other Q learning or reinforcement learning project. So in this case here, like the best result we get is with a gamma value of 0.3. So from this test here, we can choose a gamma value of 0.3 and keep on using that for the next couple of tests. And if you go down here and see like the training process from the first 15,000 episodes, like we can see that it gets a bit more flattering here, because we're only taking the average over 100 episodes now instead of 1,000 episodes. So we can see that in the start here, it's kind of like learning the same and at the same speed. But like we can see when it comes up here at like around 10,000 episodes, we can see that the red one here, it already starts to convert towards the 65 maximum expected return here, where the green one and the blue one is still keeps going up here for the first 15,000 episodes. But like the green one here is a bit more stable than the blue, and which is flickering a lot more than the green. So we can see that from here, and we just get a more stable and a better result by choosing a gamma rate of 0.3. So this is like how we can plot the data and get like data from our training process. We import it into the Python script here, just run it, change some of the parameters, tune the parameters, and then we can look at these graphs here and see how does the different kind of values affect our agent when it's training. And then from these graphs here, we can actually like do some like conclusions on which values are good and which should we try a bit more, and we can also like still tune these parameters a bit more. And also when we tune some of the other parameters, those will also affect some of these parameters here. So we can always just fine tune our parameters a bit, but from these results here we can just see and also like say and conclude that a gamma value of 0.3 here is a lot better than choosing gamma value of 0.8. And then when we tune some of the other parameters, like we can go back again and try to test like a gamma value of 0.8 and also like a gamma value of 0.5 when we have tuned some of the other parameters, and see like if this result is still the same, or if like maybe the gamma value here of 0.5 it will be a bit more stable when some of the other parameters are changed and stuff like that. But this is just to like get a fast tuning of your like agent, and also like just to get some result. And this is a pretty good result, and also like just it's not always like this good. These results are not that good all the time, but this is a pretty good result, and you can just like play around with some of the parameters and just change them and just run this Python script here, and then you can see like how the agent performed while training. So we're going to do this test here for some of the other parameters as well. So we're now back in the slides here, and I'm going to show you the other test results for the other different kind of parameters that I've tested. So I did the same thing for these tests here as well with the learning rate and also the epsilon decay rate. So first of all, I went into C++, changed some of the parameters, trained the agent for 30,000 episodes, saved the results in a CSV file, and then imported and ran the Python script, and then it plotted these graphs here. And then for the learning rate here, we can see that if we have a learning rate of 1.0, we will just converge here, and we will not get a really good training result, because when we have a learning rate of 1.0, we're taking 2 big steps when we're training. So it will not yield in any good results, and we can just see here that it is just flickering down here, and we don't even learn while like the agent doesn't learn anything, and it doesn't really matter like how many episodes that we're going to train our agent on. We're taking two big steps for the agent to being able to learn. So we can see like a learning rate here of 0.1 and a learning rate of 0.01 is a pretty good learning rate. Like we can see that we learn pretty stable, and we have a nice curve here, and like a nice graph here that is just going up steadily. And we can see that there's not that much flickering around, and we can see that we converge up here again towards like 73 on the average, which is also like the theoretical maximum expected return that we can get. So we can see that the agent learns fine here if we have a learning rate around like 0.1 to 0.01. So we can choose one of these learning rates here and tune some of the other parameters and see like how does they affect each other. And we can also like see over here to the right, when we're only taking the first 15,000 episodes, we can see that we're learning nice and steady here with the blue and green plot here, but the red here is just flickering around, and we won't get any good results because our step or like our learning rate is too big. The last test here we're doing is the epsilon decay rate. So it is the trade-off between exploration and exploitation, so for how fast our agent will learn. And I tested it for these different kind of values here, where we have the first one here is the red one. So we're decaying really fast in our epsilon value, as we can see here on the graph. So first of all here, we can see that we get a really fast learning. So we're learning really fast with epsilon decay rate of this value here. So we can see that we converge really fast to like 73 here, which is the maximum expected return that we can get. And we can see over here to the right that we actually like converge towards that value after even like only 2,000 episodes, where the other epsilon decay rates here, we first converge towards that value like not even at 30,000 if we have an epsilon decay rate at this value down here. And for the blue one, we can see that we converge around like 12 to 14,000 episodes. So the red one here is learning really fast, and the green one here is learning like too slow. But the blue one here is again like it's a nice and steady growth here in the learning and also like in the expected return. So it's like a trade-off between like how fast we want to learn, and also like we don't want to learn too slow. So it's still kind of a trade-off here, and I will say like we can choose like an epsilon decay rate between the blue one and the red one here, and probably like something around the middle, about middle of these two values here will be the most optimal value for this test here. And at the bottom graph here, we can see that I've just plotted the epsilon decay rate, so we can see like how fast the epsilon value decays over the number of episodes. So we can see that here it doesn't even converge towards the minimum epsilon value for 30,000 episodes with the green epsilon decay here. And the blue one again is not just a nice and steady decrease here in the epsilon value, and the red one is just like it's just really fast at learning, like the epsilon value just decays really fast. And again, like all these graphs here just come like back to that the most optimal value here will be an epsilon value, or like epsilon decay rate value of a value like between the red one and the blue one here. So we can use these results here to like find the most optimal epsilon decay rate, and we also found the most optimal learning rate, and also the most optimal gamma value, which is the discount factor rate. So we can see that when we have these results here, we can see like for the gamma value, we could choose the gamma value between like 0.5 and 0.3, and for like the learning rate here, it doesn't really matter if we choose like 0.1 or like 0.01. So we can choose a value between those two here as well. And then we can also do it for the epsilon decay rate, where we choose a value between the wet one and like the wet one and the blue one. And then when we have chosen the most optimal parameters, or like find some of the most optimal parameters, then we're going to do this test here again, and look at those results that the most optimal parameters yielded, and see if that fits, and if that is suitable for our application. Like how fast does that agent learn? Like does it learn too fast or too slow? And does it convert towards the maximum expected return that it can get? So the last slide here is where we're actually like going to see the result for deploying the agent with the most optimal parameters. So I chose the most optimal parameters for this application and for this agent here, and then I trained it again for 30,000 episodes. And then the results for that training process, then I deployed the agent and saw like what path did it take from one initial state, or like from one initial room, and then from a given number of fixed time steps, which in this case here is 6 time steps. So how much the reward can the agent get by taking 6 actions in the environment here? So the first test here, we're just going to go over a couple of the tests here. So the first test here, the initial state was room 8. So we started in room 8 here, and then it went to room 5. And from room 5, it saw that room 7 would return the maximum expected return for the next action. So we went up to room 7 here, and then when we're in room 7, we have to go back to room 5. And then from room 5 here, it went down to 9, and then to 10, and then back to 9 here again, which overall resulted in a maximum received reward of 70. And if we take another example here, where we have like the most optimal path, and the path that will yield the most expected return from the environment here, it is when we start in the initial state like 0 or 10. So if we start at the initial state here, 0 in room 0, we will start with getting a reward of 25. And then from room 0 here, the agent will choose to go to room 1. And then instead of going to room 2, or like instead of going to room 2 or back to room 1, it will now go to room 5. And then from room 5, instead of going to room 6, for example, it will go to room 7, and then back to 5, and then to 9, and then to 10. So this is the most optimal path to take if it starts at room 10 or room 0. And we can see that this is the most optimal path to take. So our agent has actually like learned the most optimal path by just interacting with the environment, and then we have tuned some of the parameters. So the agent learned this stuff here by just doing all itself and interacting with the environment. So we can see that our project has succeeded, and we have like gained the thing, or like we've trained the agent to do what we wanted it to do, and yield the best results that it can take for a given initial state. So thank you guys for watching this video, and remember to subscribe button and bell notification on the video, and also like this video if you like the content and you want more in the future. I'm currently doing a computer vision tutorial in C++ with OpenCV, and I'll run the data storage tutorial in C++ as well. So if you're interested in one of those tutorials, I'll link the one up here, or else I'm just seeing you next video, guys. Bye for now.